Hey everyone, and welcome to this Forge College Explainer. In our previous lesson, we talked all about preserving your contract's core invariants. Well, today, we are officially putting pen to paper. We're drawing up with actual blueprints for a big migration over to Solana. So, let's get those schematics ready and, fingers crossed, let's avoid accidentally mapping our users' funds straight into a black hole. Here's the master schematic for today's build. We're going to cover the great storage migration, dive into location, representation, and authority, translate balances and allowances, check some IDs for authority, talk about why size matters when paying rent, and finally, we'll draft up the actual blueprint.
All right, let's jump right into Section 1, the Great Storage Migration. It is officially time to break out of that old EVM mindset.
Let's think about the EVM model for a second. Honestly, building an EVM smart contract is a lot like having a giant mansion with this one infinite magical closet. You just toss your variables in there, right? 32-byte slots, globally addressable, and completely hidden inside the contract code itself. Pretty easy. But moving over to the Solana model, it's literally like moving to a master-planned community. There's no magical infinite closet here. Instead, every single piece of state needs its very own explicitly labeled, specifically sized storage shed. And on Solana, we call those sheds accounts. You actually have to explicitly pass these accounts right into your instructions. So yeah, it's a completely different way of living and building. Moving on to Section 2, Location, Representation, and Authority. These are the three pillars of translation.
Okay, so for every single EVM artifact we want to translate, we have to make three very concrete decisions. First up is location. Ask yourself, which specific account or set of accounts is actually going to hold this data? Second is representation. How exactly is this data serialized and laid out inside that account? Like, is it a fixed size struct or maybe a variable length vector? And third is authority. Who is actually allowed to mutate this data and how does the program verify that authority? Seriously, if you can answer these three questions for every single variable, you are already halfway to Solana.
Now for Section 3, translating balances and allowances. Let's talk about moving the valuables.
So when we're mapping these concepts, think about your standard EVM contract storage slot that holds persistent variables. On Solana, that simply becomes a single program data account. And why is that? Well, because it keeps those variables nicely centralized for your logic. But what about that classic EVM mapping, an address to a UNT256 balance? Here, you generally have two choices. You could use a map inside a single data account or, and this is much more common, you can use explicit per-owner program-derived addresses. We call those PDAs. And what if you have a nested mapping, like an ERC20 allowance? Well, that translates into entirely separate delegation accounts on Solana. I actually love this because it makes inspecting and revoking permissions entirely explicit and super clean.
Let's zoom in a bit on that balance mapping decision. When you're choosing how to represent user balances, you really have to weigh two different architectural patterns. On one hand, using per-user PDAs partitions the accounts. This gives you incredibly high concurrency, because transactions touching different users can run on completely parallel tracks. The catch? It requires managing a lot more accounts. On the other hand, using a centralized account gives you just a single data vector holding everyone's balance. Now, this is much simpler if you only have a handful of holders, but it causes massive right contention. Imagine 10 people trying to trade all at once. They literally all have to wait in line to update that single centralized account. So, for high volume, that partitioned PDA approach is absolutely your best bet.
All right, Section 4, Checking IDs. This is the authority translation, where we replace our old friend msg.sender.
In the EVM, the environment kind of magically knows who called the contract, right? Good old msg.sender. It's completely implicit. But authority translation on Solana means replacing that implicit knowledge with very explicit checks. Think of Solana like a strict bouncer demanding a cryptographic ID. No ID, no entry. If an instruction mutates an account, the program must explicitly require the expected signer public key right there in the instructions list. Or, alternatively, it has to use carefully seeded program-derived addresses. This allows the program to mathematically assert authority without the user needing to manually sign anything. So the bouncer is checking the math, not just some implicit caller context.
Okay, so this explicit, master-planned architecture sounds incredibly secure, right? And highly concurrent, for sure. But it kind of raises an uncomfortable reality about moving into this new neighborhood. Who exactly is paying for all these specifically sized accounts?
Which brings us to Section 5, Size Matters. Paying the rent, because hey, the landlord always collects.
Here's the deal. On Solana, every single byte of state costs money in the form of rent exemption. Basically, you have to pre-fund the account just so it stays alive. This makes account sizing a really critical engineering constraint. You literally have to calculate your space down to the exact byte. For instance, you can't just store an 8-byte U64 balance and call it a day. No way. You have to remember the 8-byte Anchor Framework account discriminator overhead. Then, you got to add the 32-byte public key for the owner reference. So, your simple little 8-byte balance suddenly requires at least 48 bytes of rent-exempt storage. Packing your data tightly quite literally saves you actual SOL.
All right, final section. Section 6, Drafting the Blueprint. Let's create your mapping plan.
By following this simple 5-step schematic, you can systematically port any EVM field into its optimal Solana equivalent. Step 1, identify the exact invariants you need to preserve. Step 2, choose your location strategy. Are you using a single account or partitioned PDAs? Step 3, design the serialization and calculate the exact byte size and remember those anchor discriminators. Step 4, pick your authority pattern. Are we doing a strict signer check or using a PDA? And finally, step 5, plan the life cycle and the rent. Who is funding the account creation, and how do we actually close it out to recover that rent later? If you stick to these 5 steps, you'll have a rock-solid translation document ready for your engineering team.
And wow, that brings us right to the end of our schematic. These mapping notes are absolutely vital inputs that you're going to need for our next lesson. I highly encourage you to visit forge.college to dive even deeper into this capstone module and explore some other fascinating Web3 topics. Thank you so much for joining me for this Forge College Explainer. So, now that you've got your schematics, what's it going to be? Are you going to build a single program with PDAs, or maybe integrate with the SPL Token program, while your blueprint holds the answer?